and providing us a holistic view of that. Dr. Sanjeev Pannala is working as an assistant research professor with Energy Systems Innovation Center at WSU. His research interests include distribution system resiliency, data-driven algorithms, ADMS, integration of microgrids and DRs, and real-time studies. He worked on the India-UK HEAPD project from October 2014 to January 2018 to earn his PhD at IIT Roorkee in India. Later, he joined as a research associate under the UISS project at IITR India from February 2018 to May 2019. He received the Doctoral Postsoco Power Systems Award in 2020 for contributions during his PhD. The Best Paper Award is at IEEE National Conference ICAER India in 2013, and a runner-up certificate for RT-RMS tool in the Resiliency Week Conference Competition 2020. So let's welcome Dr. Sanjeev Pannala, and back to you.
Thank you, Anamika. Okay, thank you everyone for joining this seminar. So I'll just give you the other side of it. I mean, don't think in terms of like converting directly your ideas into the deployable technologies. It will not cover the other aspect like funding side or the scope of the how do you really convert it. It will generally like how do you need to rethink about like what way you can apply your ideas into more feasible technologies in the near future. That's the major focus of this talk. Okay, so I'll just give you the like overall view is that like what is the need, what is the current need actually, why should we look at it that direction, okay, and what is the importance, and then what are the key things. I'm just going to explain like four of them, but there are like bunch out there, but I'll explain about like resiliency because that's totally a hot topic these days because of the weather events, whatnot. And the other one is like the data-driven, like everybody talks about, okay, how do you really utilize these data-driven technologies? So whatever you call it, like AI, machine learning, whatnot. So those things, and then like I'll give you the one example, like how, so all of these examples will have their connections, okay? You shouldn't think of like one problem as a single objective. So how do you really focus on like connecting all the dots in the field or in the control center, or maybe wherever you think of like utility application oriented. So that is the major focus of this talk. So now just give you the background. So where we are standing now, it's long story, okay? I'll just go like simple things. Hopefully you can see it fully. Maybe can we minimize that?
What's going on?
No, we can minimize these.
Yeah.
Okay. Yeah. So here is actually like if you really look at it in terms of the evolution of the grid, the electric grid. The first electric grid was commenced in 1882. So that is in, I mean, if you just look at the right top, this is actually the first station they commissioned in New York City in 1882, and thereafter, like it is like almost 140 years of journey that we have traveled through these things. So what exactly the invention? So if you really look at it, the generation wide, and then if you see the inventions, okay, so how the inventions actually evolved over the time, because 1740 is the first generator that was actually implemented or actually tested in Germany, and the later the things come into the field side, it's almost like it took more than 100 years, right? So you can think of it, like what is the concept, they tested it, and once it comes into the reality, so it took almost like 140 years. Again, there is a gap because 1882 is the year that was commenced. So you can think, so what is the gap there? So that took a long time because we do not have enough technologies to analyze and interpret the technologies. How do you really understand it? So those things were not there at all. So that's why there is really a big gap in there. But when you just really look at the later 1950s, you can see the complete evolution differently, but I'll explain later things. But if you think of renewables, because we are talking like nowadays, where exactly these roots come from, because it's almost 200 years ago they started with it. It's not like something we bringing new these days, but there was the technology exists long back, but we are not really focused because of the cost effectiveness, because the cost drives everything here. We are the engineers, but I mean, I can call academicians as engineers here, but generally there's a different terminology. But the engineers think everything should be driven by the economics. If you could not able to produce any technology which is not cost effective, that is not going to be available in any time soon. So that you need to think, and how exactly it can be connecting all these other assets out there. So that is another thing. So if you really think of the the renewable side, so hydrogen is different, but hydropower is actually in 80-80 that they commissioned. And then first wind turbine, if you I think I didn't add the figure here, but if you just go back to those links, it will provide you the person who implemented is the Bush. So he's actually dead in his backyard in 1888. Did you imagine? That was the first wind turbine which is producing this electric generator, electricity, and that is to supply his own electricity needs. That's it. He doesn't even like produce long, just distribute across the borders. So he is using his services. Then looking at the other ones, the photovoltaic, and then this is really long. Looking at the photovoltaic, the solar photovoltaic, right nowadays everybody's implementing, especially in southern areas of the US. So there it is like invented in 1813, but now you can see the gap the commercialization has done in 1950s. And think of it, because there is infeasibility issues. So those are why there is really a gap, because you don't have enough tools to analyze first, understand the behavior, and then how do you really operate them. So those technologies were lacking back then. So that's the other issue. Now, if you look at fast forward now, and then if you look at okay, where we are now. So we have really a good variety of the sources. If you think in terms of mixes, and then if you really focus at the goals wise, okay. So now we are trending towards the clean energy goals. The goals wise, it's a 2030 is the net zero, and then if you're 2050 by complete net zero emissions from all the utility sector side, the net zero energy side. So and if you think of the EV side, so EV policies are completely varies from state-wise, but if you look at it, our state is actually the 2030, we are not allowing any fossil combustion engines running on the roads, or maybe sales will be stopped by that. So that's kind of early goals. But what actually these goals are tied with our talk here, because if you think something which in the 200 years ago, because that's where the gap was, but now we are driving everything in short period of time, because you have to make everything work in that short period. So that's the focus of this one, because you have to connect what the existing infrastructure is. What are the generators you have? What are the distribution facilities you have? Or the infrastructure transmission side you have? How do you really connect it here and make sure that you will adopt the complete clean energy goals, so you could able to achieve by the target years? So if you think of the current generation mix, on the right top, you can see this. Still we are dependent on most of the if you see the coal, so you can see the pattern from the 1950s to 2020. So you can see the decline in the usage, but still it is significant enough. So still you need to think of how exactly we can retire them, and how do we really replace with the clean energy. If you think of the bottom side of the figure, so here the bottom side, you can see only the hydroelectric is dominant, and then next after that is the wind. And we didn't have much contribution from other resources, what you see. And then how do we really fasten these deployments? So that's also talks about in this one. So how do you really connect it, and how the operation side, what are the challenges we have? So everything I'll cover it. Now, what is the need now? So because you have issues back then, now what are exactly the things you have to focus now, to fulfill these gaps? And you have a shorter time to accomplish all these things. That's why you have enough scope to work on. So here, the current problems wise, if you look at it, the modeling is the biggest issue right now. It was there in the back then, because there was really mathematical based modeling, they used to have it. But right now the modeling is more in terms of the dynamic side. How to really accommodate all kinds of these dynamics. Dynamics, I mean, from the converter dominant the microgrids, or you can see the DERs, and then the conventional side, because you're keep pushing the retirement of the coal plants and the natural gas near soon, you're not going to have the enough inertia. So how do you really accommodate those criteria in these modeling tools? That is still lacking till date. Nobody really have any tool that can assess the complete inertia of the system. There is analytical tools, but not many that can analyze from transient, dynamic, and steady state completely together in one platform. So that is the one where everybody has to look at it. Then the other problems are operation side. So what is the operation side is, first you can think of as how do you connect it? What are the integration challenges you think of? Because if you look at it, at least take the Pullman example, because we don't have enough solar installations here, even though we have one in our campus, 72 kilowatt of it. But if you think of the residential side, because they're still lagging, because one is the lack of knowledge and the awareness, and the third one is the issues, because they're not well sure of how do you really they can mitigate it when there is a sudden drop in the solar generations, especially if you like think of 100 customers are there connected on the single utility feeder. So, and if that can contribute to like megawatt scale, that is unimaginable at this point of time. So that is still, it's growing. I mean, I didn't say that the things are working out some cases, but some cases they are having like a short outages. Still, everything is evolving in stage. So you have a lot of scope on integration side, especially the field side. Also, you have integration means you need to comply with all kind of fire and safety, because there are a lot of issues coming from the battery installations. So battery has like a fire hazards if you're not properly maintained, if you're not trained the people. That's why the utilities are still backing up installing large scale of battery system. That's one more lag. So, and the control side, so okay, because they are not well trained for all these technologies, because they are more actually depend on the single or maybe the vertical system, because the generation is somewhere else, and then they import from the transmission network, and then they operate at the utility side, because utilities always used to operate at the utility scale, and they couldn't worry about like what's going on the upstream level. But right now it's not like that, because you see the lot of the DR penetration at the grid edge side, that means the customer side, as well as the commercial vendors or maybe the commercial customers, for example, Amazon. So Amazon keep pushing on the EVs deployments. But if I just take the Seattle example, so they have the workshop hub, I mean, like as a warehouse hub near the Everett. So they are like almost targeting for 10 megawatts of installation of EV charging infrastructure. Think of 10 megawatt on one utility feeder section. That's huge, because how are you really going to manage it? Because the utility is not ready for it. So everybody's train is on the conventional system. So that's still a challenge. And then the communication side, the communication, I mean, is the infrastructure, because there are a lot of protocols. Like every time you come up with the different protocols, and then you just change it in order to make it more secured. And then right now, like previously, it was like most of the time they used to have like the Modbus. Modbus was generally used for the DRs. Now we are just changing for the DMP3 side on the substation side, and the Goose protocols, and then now we have CAN bus on the battery side. So these communications keep on changing, and they're upgrading it. It's not like, okay, if I just take the PMUs, wide area measurement side, they have the 1.0, now 2.4 framework has already out. So there are different frameworks are coming up and different way to upgrade it. So who exactly like taking care of all of this? Because none of the utilities trained for it. They're just still in the scope. I mean, they're just still in an evolving stage. Then cooperation and coordination. What exactly this means is, this is really important. Cooperation coordination means, suppose if I am the utility and I have my neighboring customer is commercial, or maybe the industrial person or industrial consumer. So how do I need to coordinate? Because they are going to put a lot of PVs, or maybe the winds if they have enough landscapes nearby, or maybe if they have enough space for the battery installation. So they can put it anything they want, but there is a restriction, because how do you really leverage? You can put it, get the permission from the state legislation, but you can't really operate with the same utility feeder. That you have to cooperate with your own utility nearby. That's the cooperation we are talking about. Coordination means, okay, how do you really leverage the mutual assets? So what are the assets we have on the utility side? How do they can control, not exactly the control, I mean, at least we can able to like access the monitor some level of the integration side. So that's actually the one the industry is struggling with. The cybersecurity, yeah, I mean, I don't have to talk about this one. This is really a potential threat to the grid. We have seen a lot of cases, including the Ukraine cases and whatnot. And these cybersecurity is more an issue in case of the extreme events. Why I'm saying the extreme events? Because when there is an extreme event, so all the substations will be, I mean, assume that the substation will be rushed, was flooded with that, and then you need to restore it. So what happens when you restore it? You just give it to the third-party vendors. That means you are going to give an indirect access to any firm that might not be capable enough to handle it. And if that causes any direct intrusion, or maybe the malware, when they're restoring back, that's where the situation is really challenging. So and the planning side, yes, the planning right now, what we are think of is just the 10 years plan. Generally they do it. So starting from now 2022, so they generally do it for 2032, and then they keep releasing their integrated resource planning and whatnot. So that will look at like 30 to 40 years down the line. But what the problem is, they always state the growth as a fixed 0.2% growth, or maybe a 0.5% of the growth in the load. or maybe the installation wise. Okay, they say like 10% of installation will come in the residential side or maybe the commercial side, but they didn't really think of operation side, because this is planning means something they can just forecast to a certain level, but they can't really connect it on the operation side. So, and then the policy side, because policies are keep changing. You heard of the FERC 2022 2222, and the new FERC order has already come up. So that each year the policies are changing, but the planning doesn't take care of it, because the planning is totally a different study. So how do you really they can embed these things a part of it? Resiliency assessment, and then the pictures looking at the bottom, you can easily understand. So the weather events, so there are different types of weather events we are struggling with. So how do we really enhance the grid resiliency? How do you really harden it? So those things, the interdependent analysis, this is really a future of the topic, because you have to consider everything that you're connecting with. It's not only the electric now you need to connect the natural gas supply to it, and what the heating side. So everything you need to connect and then analyze, because when you're going to a world which is connecting everything through the power, you're not going to you're not going to the world which is not imaginable without the power. So that's kind of the strategy we are in. So you might heard of some of the tools or some of the analysis is coming up recently. Maybe NARM is one, which looks at the North American Resiliency Energy Model that considers the 4 infrastructures altogether. So that's from the it's a laboratory collaborative work. So they started from the DOE direct funding. So that is one thing, is only the one project I can think of right now, but that is the future you have to consider. Now the what actually the risk right now. So now let's talk about the present situations. What are the challenges we are looking at from the power grid side? The power grid side, we have the market. So market is keep changing, everybody knows, because right now we don't have any market in the Northwest, especially. We have the Southwest, we have the California, so that operates the wholesale market, but we don't have any market. But we have the market called energy imbalance market. That is still coming up in the last 2 years. That's it. It's not even like evolved like a MESO or maybe the New York ISO. So still we are in a progressing stage. So how do we really understand the energy imbalance market versus the wholesale market and whatnot? The people will always talk about the retail market, and that's really, really complex, because we do not have enough infrastructure to accommodate all kind of these transitive energies. You always talk about the gridded side. So there is a future scope that everybody can look at it. Then the other is the environmental legislative, because environmental means the clearance side. Because you think of, okay, I can put anywhere like my PV in like maybe next to my campus, somewhere which is the open land is available, but that's not possible, because the environmental aspect, you need to assess it, you need to get the permission. That takes 5 to 10 years of time. Sometimes if you want to really put it on a transmission side, imagine like 20 years of plan. That's a 20 years if you are really putting a transmission line in the field. So right now, that's like previously it was like 30 to 40 years if you just want to deploy one of the transmission line through the forest. So now the legislation wise, why we are talking about the legislation is because that's the driving us, because they put the laws or the goals and whatnot, and that will make us the policies to drive these technologies or research. The load wise, yes, the load is unpredictable now at this stage, because the generation is keep increasing at the gridded side, and the load is drastically changing from the electric vehicle side, and then uncertainties keep moving. So these things, and the water, why we are talking about the water is because we still depend on hydropower. So especially if you talk about the Northwest. So we are lucky that, or maybe fortunate to have these hydropower. So we are still like a 40 to 50% is coming from the hydropower stations. But if you just go down the south, and then you think, so nothing is from the hydro. So whatever the hydro they're importing is nothing but from the Northwest. And so that's still a challenge if the water is not available enough, or maybe there is an issue in the climate changes, that is like avalanches or the snowfalls, if it's changing that drastic patterns, then the water availability will be less. Then you're going to eventually run it for the market, competing each other for the bidding side, and that will give rise to the huge price hikes. The fuel, yes, the fuel is I'm talking about the fuel is the natural gas, basically the gas supplies, because that's the near time supply you're going to compensate it, because every time you're talking about the renewables, but how do you really accommodate these intermittents or the uncertainty? That's through the natural gas generators. That's the plan everybody is targeting about. if you want to really retire these coal plants, you need to have the alternates to replace those. That's the natural gas is the second largest. It will be the second largest sooner. And the transmission, like I talked about, like there was a really a issue because you can't really say, okay, I can lay down the transmission like right now and start working on it. It doesn't happen the way you think. Energy equity, yes, the equity is nothing but like, okay, how do you really accommodate the price wise? So there are like vulnerable customers who are from the tribes or the like a low income customer. So how do you really distribute the price differences? Because I can bear like suppose assume that $1 per kilowatt, that is not true, but it's like 20 cents, even that is not even touching right now. So, but imagine the future, it may touch like 2 cents per kilowatt hour is still okay for us, but sometimes it may go like 5 cents or maybe 10 cents because of these issues. So how do you really distribute across these prices? Now coming to the technology wise, where we stand now. So if you really think of how actually the invention is going around from the past years, I mean, just look at the 2 years of the pattern. So if you think of it like from 1790s, that's where I have a record of. I don't know the before then what the patents or what the intellectual properties look like, but it's as per the WIPO, as per the USPTO. So the report says 7.8 million patents till date. Out of that is like 7.2 million are related to the utilities. Think of it. Utilities means it can be a natural water supply, it can be a gas supply, it can be heating supplies, or it can be a electric grid. So that means that's a huge area everybody can target, and we are fortunate that we are within that premises. And now if you think of like who is dominating it, just look at the like country wise. You can see these China is always dominating in terms of the technology innovation side. And then recently, if you just look at the category wise, okay, this is interesting because if you, so if you just look at it, the technology wise, you can see the second, the first one is the computer. That's the dominating one overall around the world. So this is the world statistics, that one you're looking at from the bottom of the top figures. So this world statistics say that like computer technology means that drives the software side or the methods, machine learning, AI, everything is actually the dominant. So everybody's keep pushing their patents on the how do they really utilize in the utility sector. And then if you look at the electrical machinery side and the digital communication side, they're actually the second dominant and third dominant. And then you can see the transportation is the third. But actually, if you look at the country wise, who is contributing on which category first, so that you can see the column wise, the China is actually contributing toward the computer technology, and the US is also the for their preferences the first from the computer technology side. But still, we are like far behind the China. I mean, if you just look at the statistics wise, the world statistics said like more than if you see this one, the statistics wise, you can see the 45.7% of the world total coming from the China side. That's huge, the technology side. That means they are capturing everything on the invention side, and we are, I mean, being in US, it's still the second, but we're still lagging behind of those technology inventions. So that's where we are going to fill in. I mean, I'm giving an example from Dr. Mani. So he has one Ukraine technology that was actually patented, and now they are commercializing it. So this is one example I'm just giving as an how can we think of now, make it as a commercialized technology now. So now I'm just moving ahead with the different phase. So here, I mean, I just skip these things. You already know these events and whatnot, what the outages are, how these varies across different borders. So I just give you the two examples. One is the cold that we have in July 2021. That's outage. Cold is the February 2021, and the July is the summer hot June. So these you can see the pictures in there. So I'll just skip that. But how exactly like we can integrate these tools? Okay. So if we have something resiliency call for the operation side, okay, what are the things you need to look at it? This is just an example. We are working with the Colorado electric grid, so we are going to deploy in their field. So what are the challenges now we are facing it? I'll talk about the lessons learned from those deployments and how do you really think of when you are thinking something as a single objective problem. What are the factors you need to consider to make it more complex, not more complex, I mean, make it more feasible technology, or maybe you can patent it and then you can work it as a deployable, or maybe even you can come up with your own firm. So that's kind of the focus now onwards. So here, if you see just the grade wise, okay, maybe I can just say that, okay, this is the grid, assume that this is the grid, and this is like a completely aggregated model of the electric system. So if you see, all the assets are actually being captured from their field system. And see this, so it has like a controller. Maybe you can think of that as a controller for the microgrid side, or maybe you can think of the control center side, because they have only one controller that distributes to the PLCs. So this controller has to be integrated with the different tools you already have in place. What they have is like one is on the energy storage system optimization, because they have the storage unit there. And there is actually, it also coordinated with respect to the diesel generators they have as a generation, along with the hydro plants what they have. So it has to like really optimize what the resource they have in the field, and then it will give you the command set points. So now these, if you look at the data side, the AMI side, what is the usefulness of the AMI is we will capture the outage scenarios, and then we could able to monitor, okay, what the consumption levels are and how exactly where the outage location, we can easily trace it out. And then if you PMU, so you can see the high frequency oscillations, what the disturbance caused by these DERs, because they also have the DERs like much smaller scale, but still the battery energy storage is significant enough to produce a lot of oscillation, because that is acting as a grid support services. That's very rare in the field. Grid support, I mean, is like it is actually coordinating with the diesel generators and hydro generators to keep the frequency stable zone. So because this is a completely remote power system, they don't have any transmission connecting together. It's like completely isolated a power system they're operating it. So it's a small co-op. So now the challenges wise, what we actually had issues when we are trying to interface these resiliency. What the resiliency, I'll just focus on the later side, but the resiliency is mostly looking at like how do you really assess the system. Okay, so by looking at what the information you are gathering through the AMIs or the assets, then how do you really take the decision with respect to the so how do you really take the decisions through the microgrid controller? So the best thing, one of the issues is, like, first thing is the data interface. The data interface means everything will be dumped to a one central database. But the processing side, that's huge. The processing, we can't really use it as it is. Then the forecasting is different. Then the estimate, I mean, the real-time operation dispatches are different, and the measurements are different. At different intervals, you have a different time mission. But what we did is like we averaged it and we kept it like a 15-minute interval as a standard for interfacing with the resiliency side. So that's one challenge, and the other is like the coordination side. Okay, because resiliency analysis assess the system condition. Okay, but it will give you the dispatch points to the other assets what you have during the extreme events. In those conditions, the biggest issue is you can't really know what the optimized value is coming from your existing tool and what the value you're proposing. It contradict each other, because the optimization what generally runs in their field is look at, say, the economic operation of it. Every time it's keep pushing it like economic operational mode, but it doesn't like consider what the resiliency is. Resiliency means you wanted to like keep some of the assets aside because when you know that there is an incoming threat, maybe because these cardio always see the avalanches. That's very often for them. And the earthquake is very rare, and tsunami is likely possible, but that's like I can't really comment on like how soon or how late it can happen, but it is like 30 years, 40 years, maybe near future, but it is for sure because they have the plate chips issues. So, and then the extreme cold event side. So if it is even a slight increase in the snowfall, then that will lead to the other issues on the operation side because the increase in demand side. So now just if I look at the tool side, so how we did it like as a standalone, because if you have the concept called like if you have a metric developed, okay, if you want to assess the system. So for that, right now there are a bunch of tools out there, open source. Everything is open source, right? Because whatever we use is like Python class for the front end interface, and the MATLAB is for coding, but Python is, again, you can convert it back. And the database is PostgreSQL because that's open source. MongoDB is there, that's open source. So you have everything as open source. So you can easily convert your research outcome into a tool or a framework that can go into the field, or maybe at least you can test it in a control center environment. So here you can see the interface side, because you can't really connect. The first thing is none of the utility or none of the control center will allow you to interface with their own databases directly. Either you need to come up with your own standalone. So that's why we propose the standalone database that can just take the data from there through a secure channels Okay, right now we propose and we're just using the IP communication base, but you can use the DNP3, or you can use the other ways to import or export the data side. And then the next challenge is, like, once you import the data, how do you really ensure that the data is correct? Okay, data integrity is right, or maybe the sampling is correctly important, and then the accuracy wise. So those checks will be done in the later stage, and then thereafter now we are going to assess these codes. Whatever you, I'm not going into the details of the metric side, but I'm assuming that you might know that the assessment will be done with respect to the network information, with respect to the measurement information, and the generation side, load side. So these are the factors we take in, and then we'll assess the system condition. So that is like what we are derived in the code. Generally, you do it everything in terms of the MATLAB or Math, Python, or what are the libraries you can use the pandas libraries for the not optimization, for the other side of the machine learnings. So those actually will be assessed through your code, and then you will be reverting back to the database, and the database will have a connection directly to the front end. Why do we need to produce a front end is, again, they can't allow you to put it like in their own front end interface HMI. You need to produce your own HMI that can be visualized altogether, and then they will be kept like a 2 parallel screens, and then they can see there what the existing operation computer is, and then you can just put it the one next to it, and then they can assess it whenever they have some see an issue from the incoming thread side. So that's what the HMI, it's like a user interface you can call, or HMI you can call it, the same thing. And then now you can see the interface like RTAG. So RTAG is nothing but real-time automation control. That's a microcontroller from the SEL. So they have in the field. So that is actually going to be interfaced. So this one, if you think of like how we developed it, this tool. So these are the details. I'm not going to touch in depth because I don't think I can able to cover the rest of the topics. So you can see the power flow side. That's one aspect of the power system, but rest of the things are from the computer side, because you need to interface. One is visualizing it. So visualizing is through the HTML. We use it, but you can use the different ways to do it. And the RESTful APIs, we actually coordinating for the data requisition, for forwarding side. And so this is actually the layer wise, if you think of exactly. So the one is a user interface layer, and there's a middle interface layer, and then there's the data layer, which is actually coordinated with respect to the data imports and exports, and then storing and analyzing it. So I'll just keep this one, and then I'll just go over the overview of it. And then this is how you can think of. So it has to embed with respect to the other tools what are available there. This is just an example we come up with. So here is the utility network. It has the ADMS, or you can call it DMS as well. So you have the SCADA, and you have the DPMUs, you have the AMIs, and you have the generation. So, and everything will be pushed into the database what they have. So assume this is like already a control center operation room. And from there, so how you're going to interfaces. Okay, so you are taking like 3 modules we are connecting together on their system. So one is on the outage detection side. If they don't, assuming that they do not have the outage detection algorithm at all, because they're still deploying the AMIs. So now we are looking at the outage detection through the feederhead meters, and there are some meters at the commercial consumer side. So, and then the other one is like, how do we really reduce the burden from the operator side? So NLP is natural language programming, because you can use it for the query side, like how do you really make it a voice query or the text query, and then it will pop up with the results from the databases if there is a huge amount of data is involved. And the other one is actually the resiliency tool. So the metric wise, like once you know the system condition, so then how exactly you're going to assess it. So this is the tool that I'm referring to. This is called real-time resiliency monitoring and operational decision support. So this is, if you look at each wise, the sections wise, you need to first have the system information, and then later you need to go for the assessment side. Okay, one is the real-time side. How do you really assess it with respect to the system conditions, infrastructure conditions, what the switcher status is, and what the load status is, and what the generation status is. So based on that, and what the event progression side. So before the event, during the event, like there is a stages. How do you really assess it? Because each state will require the different assets information. For during the event, you need the present generation, present loss, present last load. How many loads you lost it during these events, and what is the other infrastructure? What way you can reconfigure it? Whether you have any tie-ins, the backup lines you have it, or maybe you have the backup generators, mobile generators. So these are the things you look at it for the during the event side, and then pre-event side is completely different because you always think of, okay, it will be going to hit at one end of the zone, and then you'll be need to accumulate all the resources. So and then the post event is completely different because based on the damage assessment, then you need to employ or maybe deploy your field crew nearby the field crew centers, because you have like a dispersed location of the field crew. It's not like something only one location they'll put it in. So then now moving on to the tool side. So this is the actual application side. Just one example where we are going to showcase is the outage. If there is an outage, how exactly you can see this. There is like distributed outages you can see on the right top bottom. So, and then what are the locations you can pop up, and then how do you really preview it? And then these are, again, we enabled it. So these are not actually exist in their own tools. They have only like, they can just call the operators and they say, okay, this is the outage you see, and then they will send their linemen and line crew, and then they will, okay, assess it, what the damage is, and later they will send it the repair crew. So there is a really lengthy gap. So what we did is actually like, if we could able to get the data from the AMI side, and we can easily locate it, and what the other options we can see it, so that we can assess, and then we can optimize the field crew deployment. So that's a decision support side. I mean, it's like decision support means what are like proactive decisions. You can just predict it, what the incoming threat is and what the asset damages are, and then you can propose the reconfigurations, or maybe you can just the reallocation of the resources, so whatnot. So that is the looking at the decision support side on the algorithm level. So this is one example like we did with respect to the Siemens ESOT tool. So economic mode versus the resiliency mode, again, thanks to our collaborators. So here, how do we really assess this? Like if you just assume that there is an incoming threat on the, this is again a simplified model of the Cordova, and then you can see the actual generation and the load values are, and then you can see the interface side. So you know the microgrid operator. I'm assuming that you are deploying in the field, but we can't really test on that one. So we use the real-time simulators, and then we fetch the data from there, and then we created different scenarios in those simulators. And if you take the two operation schemes, so by default, you just go ahead with your optimization or maybe the economic mode of operation that always stays, okay, just keep using the diesel generator. You shouldn't use the batteries. Because the batteries are not economical if you just look at it in terms of the operation side of it. But when you just think of resiliency, because if it is an earthquake, so if you see the tsunami, so the tsunami is going to hit the diesel generator. So you have options like only the hydro and then the batteries. So what actually the example it says is, so if you look at the results here, the economic versus resiliency, we are going to preserve the battery state of charge for a long time. I mean, then we'll say that once the incoming threat has actually occurred, then you can see, you can see the usage of the batteries. So how the comparison versus the economic mode versus the resiliency, you can see the improvement in the resiliency of the grid. So that means if you have enough resources that you can easily back it up and you can make it supply long for those outage durations. So that's one example. And then the other example I talked about the reducing the burden on the human operator. So that means it's actually if there's so many window screens, I mean, this is the typical room, you always think of the control center if it is a really big utility. But if it is a small co-op, maybe like a slightly less computer, but still you can see the two people operating in the control center. Two people, one is actually looking at the dispatch side, another is looking at like a short-term planning side. Okay, so if you think of this one, so here it is actually the burden means there are a lot of things, like every time, like everybody is coming up with new methods of tools and new frameworks. And then in terms of those, how do they really dig the information? So this is just simple case. We come up with, this is an NLP based digging the data. You just made the query in the terms of text or the voice, and then it will pop up with the results. That's the thing application we have made it as embedded with respect to the resiliency tool. So this is just a demonstration. So what the node voltage has the lowest voltage, then we'll give you the results accordingly. But if you think of like the COVID side, okay, so this is for more on the I think so. This is more on the COVID hotspot zone. I mean, hot zones. So that means like if more people are infected with the COVID or maybe exposed to the COVID-19. So how do you really optimize the crew routing or maybe avoid these potential risk of health hazards? But that's not really possible until you see the large movement of the people out there in the street. So that's just simple case we come up with. So then this is an overview of it. I mean, we extended for the one more utility in the east side. So that's an example. And then this is a one use case. This is the another extension we call like planning and investment analysis tool. So planning and investment means how do you really assess in terms of like long term. So how do you assess it with respect to the deployment of the AMIs or maybe the PMUs or maybe the DERs. So how do you really assess with respect to that? So that is a one simple case we propose it. So you can see the more in the details in the paper given there. So two use cases, like, okay, assume that tornado is one expected outage. So in those cases, okay, if we have the batteries, enough batteries as a storage, and if they already have enough energy in availability for the short duration. So those cases you can you can see the actual improvement of the resiliency for the long term. So long term means like 5 years or 10 years down the line. So that's another use case of the T tsunami. And then, yeah, now moving on to the next side, like data driven side. I think this will be interesting for you. So the data driven side is actually what we mean data driven is now you're coming up with a lot of data from the different measurement side. How do you really utilize those data sets and make it as a tool that will help the operators? That's the kind of an application we are going to think in. So application means you might have worked on like different things, maybe the state estimation side or network topology estimation, solar forecasting, or maybe load forecasting, or maybe even like filling up the real-time dispatch side of control when you addressing the errors, the forecasting errors, so uncertainty. So these are like different algorithms you always develop. But what the problem is, so each algorithm will have a dependency on the next other algorithm, because so if you really think of something called like state estimation, you need to know the network side, right? Because network switch status. Then otherwise, if you don't know exactly the network switcher side, then it will be a problem. So likewise, every module will have a dependency, but our objective is like to target on one of the thing, and then that's really good. But when you think of really commercializing something, that's not going to work, because you need to consider the inputs and outputs of each thing. Then you can say, okay, this is my network, and these are the inputs that are coming from the next module from the DMS side, and then how you are going to really utilize them. So this is one of the example. And so we worked with we worked with the Seattle City Light through our Cricket project. So here it is actually the actual control center side of applications. You can see the MDMS, that's a metadata management system, SCADA, DERMS, and then these things are available to you. But if you think of like your individual algorithm or individual problem, so what happens is you just pull the data that you require, but you ignore what the constraints from the other side of it. So, but if you think of integrated tool, that's where actually the commercialization lies in, because utility always think of integrated tool. They never think of like something independent, because if you produce everything independent, they are not going to see as a useful case for them unless you showcase it is directly deployable with respect to the existing modules. So here what we come up with is like the integrated tool that can drive the outage management side. Like when there is a really outage, how do you really increase the situational awareness with respect to the existing data? So one is you already have the estimations. Okay, one is your estimations, I mean the load estimation or the PV estimation, you have it. And then now you need to think of the behind the meter that is still in the early stages. Sorry. So that is in early stages. So how do you connect it? So now you need to know the exact loads, and then what amount of that load will go through the behind the meter side, and then how do you estimate it with respect to the correlation methods, or maybe the machine learning methods that you can drive it like a correlating one from the upstream side. So those things actually you need to connect it from one by one. And then outage means like you need to also think of like after duration also matters in terms of the outages. So how long you're maintaining it, that outage will give you the gap in between the actual estimates versus the real values. Okay, so estimates always lag behind the real values because you do not have enough modeling capabilities or maybe enough representation from the previous modules. Okay, so that's what we address through these projects, and then we produce these integrated situational awareness that connects the load side estimation, behind the meter resources, and then topology estimation, and then the CLP is not cold load pickup values. So this will be like we tested in the ADMS environment, so that has a Seattle satellite, but this is again a modified version. We mask the actual system information here. So here we took the data from the DMS side, existing DMS side data, and then how do you really showcase that as a potential use case for the utilities. So that's what we tested here. Then I'll move on to the next one. So I'll just wrap up in the next 10 minutes. So the event data analytics, I think this is another one, like I always think of like processing the huge amount of data from the PMUs or maybe the high resolution data side. So what the challenges we learn, I mean, I'll just talk about the challenges we come across. Maybe I think I forgot to mention the challenges. What the challenges here it is, major challenges are, one thing is the issues with the system information, because the DMS, the vendors will not generally do it with respect to the planning or the design study. So that actually lacks with respect to the field. So I think they will take at least 1 or 2 years to just map the data. So one thing you always consider. The other thing is the data side. The data interfaces, okay, the data interfaces I mean is what kind of the data you are getting it from the other modules, okay? So for example, load side and the PV estimation, so what the resolution you're focusing on, each type it will vary, and then these results, if the uncertainty is licensed, and then that will causes the errors in the next modules. So that you need to consider every time. Then the other thing is the network side, because you always ignore of the design topology, because the design topology is completely different of what the operational topology is. Even sometimes the crew says, okay, I just turned on this breaker, I mean, I just turned on these tie line, but that's not actually true in the control center, because that's manually operated, and he doesn't know, because the people will get the supply, but the operator doesn't know what exactly the topology is right now there, because the mapping issues still exist in the world. So that is another one. That's why always the real versus estimates are, there is still a gap. I mean, at least you expect like 2 to 5% of errors always in the control center. So those are the challenges from that one. And then moving on to the event data analytics side. So we work with the Comet, Edison utility from the Chicago. So they have like bunch of PMUs. So they have bunch of community microgrid, and they have like 46 PMUs in there. How do you really process this 46 PMUs data? And then how do you really come up with a decision saying, okay, there is an event, there is an attack, or there is an issue, is there really an outlier, or there is a really bad data, or there is a sensor issue, or maybe the PMU detection, I mean, PMU output issue. So there are like a bunch of issues, because 46 PMUs are huge. That's not small number. Generally, what we think of the studies is like we take processing like 5 PMUs at a time, or maybe 6 PMUs, or maybe like 10 PMUs at max in a processing windows. But processing completely all the PMUs, that is needed for the utilities, because they want to look at all the data sets, and then they want to take the real-time decisions in that. So that you need to first look at the data side. What are the dimensional, I mean, how do you really reduce the dimension? You have like voltages, 3-phase voltages and 3-phase currents and angle. I mean, then you need to look at like 46, that is really huge in terms of the dimension side. So how do you reduce and then still preserve the information? So that's the one we tackled here. And the base detectors, like, okay, how do you really separate out the normal versus the anomalous? That's still a challenge. There is no standard way to do it. So there is like, people will say with the threshold basis, they will say the supervised learning or unsupervised learning based on the existing or maybe the past event sets. But there is still a huge gap in there. But I'll explain what the approach we used it here for the practical case study. And then the classification side, there is no benchmark rule for classifying it based on the signature that you got it. But how do you really make it worth for the utilities? So that's I'll explain. And then the broader level classification means types, because they are interested in the faults majorly, or they are interested in like DRs, there is any DR outage, or maybe the DR switching turned off unintentionally. Those are majorly they look at it. And otherwise, like the normal reconfiguration or the switching event, they're still okay. Even cat bank changes, they're still okay with it, because they know they changed it and there will be some oscillations. There should not be some issues unless there is an attack, like cyber side of attack. So here, this is like their system. Okay, so if you see the data wise, you can see the blue colors, those are actually the PMUs. This is a Bonneville community microgrid. Okay, so it has like a distributed energy source from the generator side. Gas generator is there, and then BESS is there, and the solar PVs are there. So you have all mixes of the sources, and this is actually worth to explore when there is an issues from the different directions. So the different, actually what we see the issue is, the first issue we come across is the feeders. There are 2 different feeders serving these community microgrids. So it has a tile in the back end, but when you look at it, the data side, if you assume that there is a connection back it, like one way, if you assume it this way, the connection, if there is an outage on the upstream side, so that is completely different analysis. If you consider the other way of the direction, that's a different approach you need to implement. And that you need to make it as generalized. If you can't make it as generalized, then it doesn't going to work, because they always switch between those 2 feeders. That's common, because when there is an outage on the upstream or when there is an issue or maintenance, of course, they have to go to the other route, what is available. So, and then the other issue we saw is like integration side. Whenever there is an issue drops, or whenever there's sudden change in the climates, and when there is a sudden change in the load side, there is really hard to distinguish. You can't really say that which is what, whether it is from the load side change uncertainty, or whether it is like really a PV drop, or maybe a best drop is due to some issues inside of the controller, or maybe the battery dispatch side. So that is really hard to distinguish unless you have to understand the real physics of the system. The real physics, I mean voltages, relation with respect to the network, and then currents and the impedances, whatnot. That if you understand, then you can able to do it. So we have some interesting results, but I'll give you the basics one, because we looked at the unsupervised. Why unsupervised is, never know what the system look like in the next decade, or maybe next year. And that will not cope up with what the supervised is, because you keep on adding the infrastructure to it, and that it will keep changing the infrastructure configuration side, and there is no standard way you can come up with. Unsupervised generally only look at the data side, and that's what they are interested in. It's not how we're driving it. It's the utility driving us to do this kind of analysis. So these are like basic schemes we looked at it. Like DBScan is a cluster, and the K-means is a cluster analysis based. Like cluster means all know about it. Like how do you like group it, the data side, and then you just make it as a one cluster, and then you analyze it within that cluster. Okay, what the anomaly, which is lying outlier of that cluster. So then you say that might be outlier, or maybe an event, potentially an event. So that's a cluster based. But if you look at it, the net OLF, this is like outlier factor based. The factor means is like how far is the one data point with respect to the other data point. So that's one other approach we looked at it, because that's what the interest to them. So, and then that, and the RSF is actually cut-set matrix, use it, and that's again, it's actually the unsupervised technique. So each technique, if you just take the one example, again, we have bunch of events we analyze. I mean, I have like test cases, like 5 to 10 test cases we analyze, and each will produce like megabytes of data. So we have that data sets. But I'm just giving one example. If you just simply look at it, one example like gas generation switching, okay, that they generally do it when there is a like needed. Then those cases, you see there is no way like you can say that, okay, whichever the algorithm works well. Okay, so you may say that DBScan is giving it, but if you see the NetOLF is giving some outlier factor, that means you can treat this as an event from the NetOLF side, method side. But if you see the DBScan still ignoring it, that is lying in the noise level, and that's ignored. So if you go with one approach, I don't think like we can give you the exact or accurate results to any utility with these 46 PMUs or high resolution data sets. So what we did is instead we could just go with the ensemble approach. Ensemble approach is nothing like combining all together and then just taking what the positives from each method side, and then you're just combining it to make it okay, if I get like a trust worth from the two of the methods, and then I can say it, okay, this could be a potential event or an anomaly. And then the other challenge is the classification, like I mentioned. So one is the dimension side, you need to reduce it, obviously, if you're really looking at like hundreds of PMUs, if you want to analyze one service territory, or maybe even if you look at the AMI side, if it can able to accommodate high resolution data, then it's just still a challenge for it. So then the other thing is like the once you know the anomalies from the detection side, so how do you really classify it? What the ways you have? The best way this is just the one way. I mean, you might have other approaches, but so this is one of the best method we come across with through the clusters. Cluster means is like, again, you will cluster with respect to the voltage and the current, because that's give you the physics of the system. And that based on that signatures or maybe the variations, then you can propose is that the switching, I mean, it could be a fault, or maybe it could be any variation with respect to the power, active power or reactive power. Again, there is no standard or there is no standard guideline that you can always compare with. This is again a relative comparison. Everybody does. So that's the other one. And then this is like just one test case. I'm just giving you an example, like what the accuracy you can think of. That's always lies between 70 to 85%, or maybe you can't even like touch 90s. That's for sure in the field. Because here, whatever the research we publish, it will be 95, 98. I mean, we have papers. I mean, we worked on the data set, because that's a really small system, and the way we interpret the analysis is different than the field, right? Because we know what the events we created, and we know the locations are. And then that's why you fine tune your method according to the known values. But what we tested is everything is unknown, because they give the unknown data to us. We don't know what the system they did. We don't know even what the labeling of the event is. They're completely blind of the system. So that's where you see the real performance that you need to think of. And then again, how do you generalize it? Generally, I mean, there is no system dependence or network dependencies, and there is no correlation with respect to the location side. So those things you need to look at it from the, data-driven algorithms if you want to look at the event analytics side. So this is one of the tool, from the Shicker and Runrock side. So just to give an example, how do you really convert it? This is just a simple Python program. You can make it and you can make it work. And then you can directly interface with respect to database. So that's how we deliver it as a package to the Comet. So they are deploying with respect to controls. And again, it takes years to go to the field. Again, it won't go in a single day. Now I'll quickly give these a field example because this is an interesting thing.
So Sanjay, we have 4 minutes.
Okay.
I want to leave some time for Q&A.
Yeah, sorry. Yeah, I think I just wrap up with this one. So the field implementation. So we took 2 years. 2 years of plan. Okay, just 2 years of plan. Out of 2 years, only 1 year just back and forth exchange of the planning side. And then that is again with the crew, field crew, what they have with the Avista. And this is like one of the VVs, like just a world war control. Everybody knows world war control is, and then it just implementation of world war. They already have it. It's something not new. We are proposing it. What they already have, we wanted to propose something different algorithm to it. And just looking at different algorithm, they took like a year to get an agreement on like how the implementation will go from idea to the field side. So how that is actually is going to happen is like, first you need to understand the the modeling side. First you need to go to the offline side. All the cases you need to know what are the extreme worst scenarios you come across and how do you really get the results for those scenarios. First you need to opt in that one, and then later you will go for the testing side on the lab scale or maybe the field equivalent stages. Then later after, like if you have field devices, real-time automation control from ACL microcontrollers or maybe the relays, what you have on the measurements and everything you connected and you have embedded your program into their RTACs, and then you analyze. Thereafter, if they get enough confidence on it, then the later phase is actually the field implementation that is driving directly into the PV inverter, and that will producing an algorithm will be embedded in RTAC, and the RTAC will communicate with the real field data. So that's really a challenge. This is like the way we are going ahead for the implementation side. This is test setup that we are going to test it in our facilities, and then the next setup is like something we are going to test in the Avista Innovation Lab. And once we get the results from this one, and then there will be a field crew and the relay tech crew that they sit together and they say, okay, this is really work to implement it, and then we're going for the implementation and programming it. Yeah, that's all I have. Yeah, thank you.
Okay. Thank you. Right, so we have only a couple of minutes. Let's open up for some questions. What is?
If nobody has a question. So just a simple question on this. So when you say you work with the utilities, how do you get their feeder model? I mean, they use some kind of commercial softwares, maybe. And then you mentioned the research that you did was on GridLab or OpenDSS. So how was the feeder transformation working for when the research was going on?
Thank you. That's a really good question because that's really important if you want to connect to the research side. So yeah, the field equivalent data. So generally they give us the design diagrams. Okay, and then you will just come up with your own conversion tools. If they have the same, you have a conversion tools. If you want to analyze for the offline case studies, if you want to do the real-time studies, and that's again hard because the real-time studies are needed for them to test it in the dynamic scenarios. For those cases, what we do is like aggregate it, because we aggregate the assets to a primary feeder level, and then we'll see the location which is important for our deployment side, and that location will be fully expanded, and there you will just do the complete modeling of it for the real time. For the offline side, it's a complete feeder level. You convert it through the same tools if you have, or maybe you can use it like the direct design planning. They just share the bunch of design diagrams, and then you need to go through each document and then implement from the scratch. That's really a pain, but that's only the approach we have. There is no direct way you can do it. Yes, there is no way like you can import some tools supported, like some co-ops use the windmill for planning studies, and then you can import it there directly into the OpenDSS or GitLab. But some can't use really those things. They use the DMS from the Hitachi, from the other vendors, so Siemens, and they don't support like these things. They support only the same format. So you have to have these conversions. Thanks to Pannala, because they already have those converters available, so you can use it.
Okay, anyone else? Any other questions? Anyone online? All right, let's thank our speaker today. Thank you, Sanjeev, for the talk today.
Yeah, thank you so much for inviting. Thank you for attending this talk.